Hi everyone, my name is Stanislav Yaroshenko. Actually, today we are going to talk about machine learning basics. Well, within the framework of today's lecture, we will talk about machine learning and introduce the concept of artificial intelligence and discuss is there any strong or super artificial intelligence nowadays? Moreover, we'll cover some challenges of machine learning which do exist right now, today, and how to cope with these challenges. In the second part of the lecture, we will be focusing on machine learning applications for power industry. We will consider some possible tasks, application areas where machine learning methods can be used. Moreover, the last part of the lecture will be covering some very important issues regarding your project case, which you were provided within the framework of the summer school assignment. Now let's talk about machine learning. And this concept is very important for up-to-date digital transformation of the industry. And we will focus our attention on some basics of machine learning and what is the place of machine learning in artificial intelligence. And we'll talk about some machine learning failures, so which may be really interesting for you. First of all, I would say that the general term, I mean, the umbrella term covering all of the spheres of information and data analysis is artificial intelligence. Actually, it is a branch of computer science that tries to reproduce human behavior in machines, in computers, or the ability of machines to reproduce this human behavior. One point to note here that robots or artificial intelligence are not synonymous with artificial intelligence too. And well, think of robots as the physical structure carrying out the decisions made by the artificial intelligence mind. And next, within artificial intelligence, inside artificial intelligence, we have machine learning, a range of technologies for computers to perform maybe some sort of cognitive functions. And these techniques are about learning from examples to reproduce the behavior that we expect the system to show. For instance, recommendation engines of Netflix use machine learning algorithms to analyze your activity, compare it to the millions of other users, and then determine what you might like to watch next time. Within machine learning, we have deep learning. This technique uses layers of artificial networks, loosely inspired by the biology of animal brains, to have a machine learn how to recognize different patterns. But what is really important in this concept that machine learning, including deep learning as well, is really focused on the data and on the data set. And anyway, whatever machine learning approach or algorithm you introduced, first thing to focus on is the data set. And that means that first of all, you have to select relevant data sources, model data, clean the data, and only then you implement machine learning models by implementing the stages of model validation, training, using, testing, yes, and finally maybe adjusting the model again, starting from the step number one. And well, what is really important here, and I want to remember it, that the most important for machine learning is the selection and preparation of the relevant data set. This is just the list of some prospective um, processes or tasks within the framework of the power industry, which may be addressed with the help of machine learning techniques. And what I really want to draw your attention to is that machine learning is widely used for scheduling and forecasting, including energy demand, energy consumption, even forecasting the generation of renewable energy sources, which is actually the topic of your project case within the framework of the summer school. Machine learning can also be applied for design and reconfiguration, And it means that machine learning can also be applied to find the best possible configuration of the power network, which is also the task of your project case. So move on and feel free to use machine learning algorithms and methodologies to address the project case in a more advanced way. Well, first of all, we need to differentiate between two main concepts, strong and weak artificial intelligence. Strong artificial intelligence is some sort of hypothetical machine that is able to think, and moreover, this machine is aware of its own existence. So it can solve not only tailored tasks, but also can learn new things like humans do. Weak artificial intelligence already exists, so it's an application made to solve specific problems such as image recognition, I don't know, like car driving, photovoltaic energy forecasting, playing games, and so on. So weak artificial intelligence is the thing that we call machine learning. And actually, we don't know yet whether strong artificial intelligence can be invented because it is not invented at the moment. But anyway, according to expert surveys, we'll have to wait maybe for 45, 50 years. And that really means someday. For example, experts also say fusion power will be commercialized in 40 years, which is exactly what they said 50 years ago. And the same goes for artificial intelligence. And I want you to know that strong and super artificial intelligence, well, does not exist at the moment. But, well, being optimistic and looking forward to the future, it will be invented and applied someday. Well, now let's talk about the problems of artificial intelligence and machine learning. Anyway, it is still unclear when strong artificial intelligence will be developed, yes, but weak artificial intelligence is already here and it's working hard in many areas. And the number of those areas grows every year. And machine learning lets us handle practical tasks without obvious programming. So it learns from examples. For more details, actually, you may Google some information regarding how machine learning works and in simplified way. And you will find that actually the basics of machine learning is learning from the data set, so learning from the experience in order to demonstrate the similar behavior. Actually, it makes machine learning models predictable, yes, because we certainly know in some types of machine learning tasks of how the model is going to behave, yes, because we train this model based on the expected behavior samples. So we teach machines to solve concrete problems, exact tasks. So the resulting mathematical model, what we call learning algorithms, so can suddenly develop something, something global in order to solve the humanity. In other words, we shouldn't be afraid of using weak artificial intelligence, but it's really important to understand that some things may go wrong. And the existing list of problems of artificial intelligence and machine learning is very extensive. And these slides presents only the basic ones. It's bad intentions, prejudice, ethical rules, false correlations, or even dirty or poisoned initial data. So all of these problems we will consider in subsequent slides. Now I would like to focus your attention on the problems of artificial intelligence and machine learning associated with ethics and maybe in more detail associated with the developers of such software. Well, even if machine learning algorithm developers mean no harm, a lot of them still want to make money. Actually, it's a reality. Which is to say that their algorithms are created to benefit developers, but not necessarily for the good of the humanity or for the good of the society of the specific country. For example, some medical algorithms might recommend expensive treatments over the treatments with the best patient outcome. Anyway, sometimes society itself has no interest in an algorithm becoming a moral paradigm. For example, Maybe there is a scenario. Let's consider the scenario that we want to find the solution. Yes, and to find the balance between traffic speed and the car accident emergencies. So we could program autonomous cars, robot cars, to drive no faster than 15 kilometers per hour. So it almost guarantees that the number of the accidents will drop down to zero, but it will eliminate some other benefits of using the car because the driving mode will be too slow. It means not so comfortable from the point of view of using car. Some parameters of machine learning algorithms typically do not include ethics. Computers by default actually don't know anything about ethics, and an algorithm can put together a national budget with the goal of maximizing gross domestic product, for example, or labor productivity, but without ethical limitations in the model, it might result in full elimination of the budgets for schools, hospices, environment, because these spheres they produce no direct benefits, so they do not directly increase the gross domestic product. But anyway, from the point of view of human understanding, so it's very important to address the environmental issues, but from the point of machine learning algorithm, it is not with a broader goal. So again, yes, addressing this example of creation of gross domestic product software. So if we implement machine learning algorithm, it may decide to increase productivity by getting rid of every person who is unable to work, which actually absolutely eliminates all existing ethical rules as well. The point is that ethical issues must be incorporated into the software, into the machine learning problem statement from the very beginning. Well, the other problem is that ethics may change over time and sometimes very quickly. And ethics can also vary between different groups within the same country, never mind in different countries. For example, in China, using this face recognition for mass surveillance has become normal. Yes, and maybe you know this so-called like global eye system recognizing everybody and everywhere in the streets. But anyway, this system, I suppose it will not suit the countries with like strong freedoms of humans because the application of this system really depends on the situation and on the conditions on where to depend, or either is it just feasible to depend the system from the point of view um, of the human living and like pace of life, personal data, like freedoms, etc. So it's a big question, and actually that means that ethical rules cannot be universal for everybody. So it makes sense. Actually, for this reason, we cannot use machine learning to incorporate, I would say, global ethics, which is suitable for everybody. What I would like to draw your attention to is the screenshot of my iTunes software. Yeah, and what's really important here that I would like to state that machine learning changes human behavior. Actually, this example is just one of the examples on how artificial intelligence affects people directly. So it recommends new movies, new songs to you based on your ratings of other films and other musics, depending on your preferences, with those preferences rated by the other users, actually. Some systems are getting pretty good at it. Well, a music recommendation system changing your preferences over time, but what is really important that it narrows your music tastes during this time as well. Because without this recommendation system, maybe you'd prefer to watch some movie or to listen some new type of music. Yes, but using the artificial intelligence, every song, every movie hits the spot. So in the end, you stop investigating and just obey and just consume the results that is fed to you by the artificial intelligence agent. So it's also interesting that we won't even notice how we get manipulated by these machine learning algorithms. So the movie example or the music example is not that scary, but consider, for example, news or propaganda. So it's really important. So think how you are being manipulated by these artificial intelligence and machine learning engines. Well, now let's focus on false correlations. And actually, a false correlation occurs when things completely independent of each other demonstrate some sort of similar behavior. Yeah, and actually, this may create the illusion that they are somehow interrelated and connected to each other. Well, for example, did you know that butter consumption in the United States correlates with the divorce rate? You didn't? Yeah, so that's right. Of course, so real people uh, relying on their personal experience and human intelligence, they instantly recognize that any direct connection between butter consumption and couples divorced, yes, for this very specific case, is extremely faulty. Yeah, so it's false. A mathematical model does not have this knowledge, this experience, because the mathematical model simply learns and generalizes data. For this reason, false correlations may occur, and we have to be very attentive, and because each outcome of the machine learning algorithm should be supplemented with the corresponding interpretation of the result that you have as a solution. The next important error, yeah, mismatch of machine learning algorithm application is feedback loops. And actually, feedback loops are even worse than forced correlations because feedback loop is a situation where the algorithm's decision affect the reality. Yes, and actually, it in turn convinces the algorithm that its conclusion is correct. For example, there was some sort of, like crime detection program implemented in California police, and it suggested that police should send more officers to like some marginal neighborhoods which were identified based on the crime rates. So the number of recorded crimes in the police database. Yeah, but more police cars in a neighborhood finally led to a situation when local residents, local people who are living there, they started reporting more and more crimes to policemen. So they started doing it more frequently because someone from police was right there, yeah, and somebody from these people just immediately reported that he or she has a problem. And finally, it led that the officers of police, they they made more protocols, more reports, so they enriched the database with a higher crime rate, and that finally resulted that the machine learning based program, the artificial intelligence said, okay, so we have the greater crime level, so we have to send more police officers to that region. So after sending more officers to that region, we have more and more complaints. So again, we are increasing the crime rate, and again we are increasing the number of police patrols and police officers in this region. So finally it may lead to the situation when all of the officers and all of the police patrols are sent to that region because we are having more and more and more complaints. So it means that we have some sort of backpropagation loop which distorts the reality because actually the level of the crime stayed at the same level, but we increased the number of patrols, the number of officers, so we increased the number of complaints, etc. So it means that machine learning application in some situation may affect the reality. Well, now let's focus on dirty and poisoned initial data. And actually, the results of any kind of machine learning algorithm depend largely on reference data, on the initial data set, and actually it is some sort of the basis of machine learning methods implementation. The data actually may turn out to be bad or distorted by accident or through some bad intentions of somebody. In case of it's like intended poisoning of the initial data set, it's called poisoning, for example, as a result of the hacker's attack. But what about street sign recognition by self-driving cars? So you know that this technology is already developed. Moreover, it is implemented for some cars of the high-level segment. Um, well, but is this technology is better than facial recognition? I would say not so much. A group of researchers proved that sign recognition is prone to faults as well, because small changes which any human do not notice at all caused a machine learning system to misclassify the stop sign as a speed limit 45. And it's not just a random mistake, so it happened in 100% of the testing samples. Machine recognized three of these defaced images as a speed limit 45 and the last one as a stop. So it means that if there is some some situations like vandalism or just spoiling the visual representation of the road sign, so it will finally lead to misclassification of this road sign by your automated driving system, so which may lead to a road emergency. And well, this is quite suspicious, and well, it provokes some thoughts and ideas regarding the possibility of implementation of weak artificial intelligence in autonomous driving, for instance. Well, now let's talk about hacking of machine learning algorithm. Actually, how massively does one have to alter the input to full machine learning? So you will be really surprised how negligible this change can actually be. To the human eye, there is no difference at all between two pictures of pandas presented in the slide, whereas a machine learning algorithm was quite confident that they were completely different, a panda and a gibbon respectively. So we've just added some white noise to the picture and have got like completely different result. Even a well-functioning mathematical model, for example, the one that relies on good data, can still be tricked if one knows how it works. For example, a group of researchers figured out how to trick a facial recognition algorithm by using special fancy glasses that would introduce minimal distortions into the image and thus completely alter the results. So, wearing glasses with specially colored rims, researchers tricked the facial recognition algorithm into thinking that they were somebody else. And these are the examples that came from my own experience of recognition of the pictures. And well, these results, these photographs presented in this slide are quite good results, actually. So you may see that in the left photograph, well, it's a dog with 95% confidence, and another is a person, yes, so it's me with, so it's not seen here, but it's a 90% confidence as well. Here I put the photograph of myself when I was recording a video lecture. And again, so it's a person with 96% confidence and a TV monitor with 79% confidence, which is fairly well as well. At this slide, I would like to draw your attention to the left photographs, first of all. So these are two my dogs, the hound and husky. And actually, both of the dogs are recognized quite well. The ginger one, the hound, is recognized with 100% of confidence, and husky is recognized with 99% of confidence. But what really happens to the right figure? uh, it's okay with sofa, but we have 53% of confidence for the dog and 59% of confidence for the cat. So it's like very surprising for me, but I suppose that it is the first living cat and dog simultaneously. Now let's talk a little bit in more detail about machine learning applications for power industry. I would like now to consider a very specific example which is closely related to the project case that you have within the framework of the summer school program. As a particular case, let's consider the following scenario. So let it be the customer, so the company owning a number of photovoltaic power plants, which are titled from A to K, so it's 11 objects, and the company sets the task to develop a system for their generation forecasting. For illustration purposes, let's consider the layout of complete data set from these power plants in the axis month and latitude. So latitude is horizontal axis and month of the year is the vertical axis. Actually, these power plants were selected primarily for greater clarity and simplicity of the outcome representation. Actually, the crosses in these metrics, these graphical metrics, they mark the data that was included into the data set, but due to the poor planning of the data collection stage, it can be seen that there is not any power plant for which the data set would contain the data for all months of the year. Yeah, so a certain range of latitudes, climatic zones is covered, but there are no data for plants B and C completely within this range. As a result, at the stage of the developing, evaluating, and testing the model, the results of the testing set may turn out to be good enough for the task under consideration, but at the same time, this model may turn out to be completely non-applicable, yes, for real practice, because we missed and we completely failed the stage of data collection. Well, the model accuracy for the entire system is shown at the right figure in this slide. And in order to demonstrate the effectiveness of using this specific machine learning algorithm, we used the R2 score, metrics as a quality criterion. And the decrease in forecasting accuracy for power plants from G to K, yeah, so it's quite obvious actually for natural reasons, because the initial data set, yeah, is here, did not contain data from power plants located at these latitudes. But due to the time intervals were different for different power plants, it turned out that despite the presence of data in the set for the entire year, the developed model cannot be applied to any of the power plants during the whole year. For example, the power plant E, actually, it's an exception. It's here. Yep. Actually, the initial data set contained data from power plants D and F, which are very close geographically to it. And the data set from power plants D and F covered all months of the year. Actually, for this reason, we had rather good accuracy associated with power plant E. Okay, so in addition, the results for power plant C were really low and it was not expected. But let's try to understand why. Actually, from the point of view of the power plant C, low accuracy occurs due to the power plant's technological specific. So power plant C contains different equipment, different inverters, different types of solar panels, and even different grid connection configuration. For this reason, the model created for the whole set of photovoltaic power plants was not applicable for power plant C completely. Actually, at the result, at the testing stage, the accuracy of the model actually was high. But while the testing set contained data for different months of different power plants located at different latitudes, we've got this very low implementation stage accuracy. And actually, it turns out that the model does not operate properly, not only for the PV plants at other latitudes, but in other weather conditions, which actually could be expected. And the worst thing is that the model demonstrates low accuracy in some months, even for the very specific power plant from which the original data was collected. For example, yeah, so let's consider this, this part. Yep, and this one. So it means actually that the model created like a universal, as a universal software tool to forecast PV production was not treated properly at the data collection stage, and for this reason, it resulted like in complete unfeasibility of using this very specific software for industrial purposes. Well, now let's consider the example of the PV forecasting regression model training that forecasts the photovoltaic power plant output. Actually, in this figure, we see a fragment of the power generation curve before data pre-processing. So you may see here that it contains large errors. These errors are highlighted in circles. And actually, after large errors are eliminated from the data set, so we have this like pre-processed data set. In the general case, such errors can be associated with some faults of measurement systems, data transmission and communication systems, maybe some errors in the program code when converting or reading the files, or even just typos made during manual copying, etc. So the large errors were intentionally integrated into the training set, yes, to demonstrate this example. Actually, during training stage, the model strives to find dependencies in the initial data set. Actually, at the same time, large errors in the data set can corrupt true dependencies and even lead to the detection of false dependencies. If the tools to control model overfitting are used, it is possible to avoid false dependencies like in model training stage, but nevertheless, large errors reduce the general accuracy of the model since they distort the values of the loss function and worsen the training process convergence. In case of false dependencies, the model may give a forecast with large errors in certain hours of solar power plant operation, as actually is shown in this figure. And in this case, such errors will be for the user evidence that the models contains wrong rules, which will significantly reduce the applicability of the model predictions, which is already like a black box due to the implementation of machine learning algorithms. In this diagram, in green, you see the ground truth. Yes, in orange, it is the result of the forecasting when the model was trained on data with larger errors. And with dark red curve, you see the forecasting results for the model trained on filtered data. Well, it's like very easy to recognize the difference. So large errors introduce great deviations of the predictions at the implementation phase of the model. The model accuracy factor selection determines how the training process takes place and how the model results are analyzed by the software developer. So at the same time, both in classification and regression problems, there is a large number of different quality metrics. Actually, selection of the irrelevant quality metrics can be misleading since it may not reflect the model quality in terms of its performance efficiency. And this figure shows a daily curve of solar power plant generation and a forecast is produced by the model, and two graphs of two different quality metrics, the absolute percentage error and the absolute error, are also introduced. In this example, when the error is inherently large, the percentage error values are low due to the large actual values of solar power plant generation. On the other hand, in the boundary hours, it's morning and evening, an insignificant absolute error leads to huge percentage error. So it may be noticed here. Yep. Well, actually, what does it mean? If we use a percentage error when training the model, then the model will always tend to give zero output, because even small deviations in the boundary hours will give very large values of the percentage errors, like more than 100%. For this very specific case, it is necessary to carefully select and analyze the model quality metrics based on the particular task, particular problem under consideration. Secondly, we need to understand what exactly lies behind the selected quality metrics, not according to mathematical laws, but according to physical and economic criteria that we take into account when creating this machine learning-based system. So what does it mean from the point of view of this very specific example? So we will get, extremely high errors for these hours. It may be greater than 100%. Yeah. As far as the resulting quality metrics is the mean average, is the mean absolute percentage error. So we will have these really high values of the error using MAPE quality metrics. And for this reason, our model cannot be recognized as effective or at least applicable for the specific task under consideration. So it means that please be careful in selecting the quality metrics of the model, because it makes sense on how you train and how you analyze the final result that you get. Well, finally, selecting a model and machine learning algorithms, which by their characteristics, their initial sense, do not correspond to the task under consideration, will lead to the model accuracy degradation. Actually, such errors are less dangerous than the errors discussed at the stage of the data collection or data analysis, since their negative effect is actually revealed immediately during the model training phase. But nevertheless, attempts to use inappropriate models can significantly increase the labor costs for intelligent systems development, and in the worst case, results in the conclusions that it is impossible to achieve the required quality indicators. But it is possible if we use another appropriate machine learning model. Obviously, in the case under consideration, the model should be able to predict fundamentally different daytime hours, including daylight time and the period after sunset and before dawn. Well, actually, the polynomial regression model is not capable to deal with such logic, since it is actually inherently a continuous function. The decision tree, on the contrary, forms a piecewise continuous function and can easily learn the logic of separating the operation and non-operation intervals during the day and night hours. But with low depths, it will not be able to accurately forecast the generation due to its discreteness. To solve the problem, a shallow decision trees ensemble can be effectively applied, and the results of the models applied to the fragment of photovoltaic energy production are shown in the figure presented in this slide. So polynomial regression cannot learn to cut, yes, the night hours. It's here. Therefore, polynomial regression goes negative. A decision tree gives two-stepped output. It's in orange, yeah. And actually, it cannot accurately describe the graph due to the discreteness. To avoid the erroneous selection of inappropriate model, it is necessary to understand the problem and the nature of the target value changes, and to know actually the mathematical nature of the models and their learning principles. And finally, not to analyze the model quality metrics, but also to compare its output with the required output. So it's very important. Well, I suppose you've been analyzing these materials within the framework of technologies of energy conversion in smart energy systems, but I will be very brief. As far as we are focusing on forecasting the solar radiation within the framework of the project case, we have to keep in mind that it is a highly stochastic and very hard for predictive models problem. Yeah, so and if we consider the Earth's energy budget, yeah, so the incoming solar energy is distributed between reflection by the atmosphere, reflection by clouds. Some solar radiation is absorbed by the atmosphere or by the clouds. Some of the some of the incoming solar energy is radiated to space from clouds or atmosphere, etc. So finally, it means that the energy potential, yes, of solar rays passing through the atmosphere of the Earth degrades greatly due to the ozone layer, like water molecules in the air, clouds, dust particles, etc. Moreover, it depends greatly on the inclination angle of the photovoltaic panels. As far as in this case, we will have the reflection phenomena, and when we have the angle, when it is not direct, so it's not 19 degrees, so we lose some energy from the incoming solar energy, and it means that we can produce lower amounts of the electric energy from these photovoltaic power plant. Well, it is worth noting that PV panels may be of different types, representing various characteristics like efficiency factor, degradation factor, temperature coefficient, etc. But what's really important to notice here that the capacity curve, so the output capacity of photovoltaic power plant, depends greatly on solar irradiation and depends greatly on the temperature. Well, generally it means that PV panels installed in the northern pole so will be more efficient than PV panels installed in Africa because at northern pole so we have great like cooling environment, yeah, and it means actually that we may improve the efficiency factor of the PV panel. But from other point of view that at northern pole, we have polar nights, so the daytime is very short, and for this reason, PV panels may prove to be not so efficient because sometimes there is no sun completely. Well, speaking a little bit more detail about the problem represented in the summer school project case, as far as we are dealing with PV panels power generation forecasting, it is worth noting that forecasting models can be considered within the framework of two important criteria. So the first important scale is the prediction time horizon. It corresponds to very short term, and middle term forecasting according to this curve. And the next important feature is the, I would say, the area, yeah, for which we are providing these forecasts. So global, yeah, corresponds to the area like of big territories, of countries, like great regions, districts. Some mesoscale corresponds to some smaller areas, maybe the territory of the very specific energy district where the power plant is allocated. And microscale, well, it typically corresponds to the application of models which are able to predict the energy output of individual PV panel. Yeah, and actually this diagram represents the technologies and methods used for PV plants prediction. It's like the state-of-the-art diagram, and it's quite understandable that for like um, I would say day ahead and more um, prediction horizons, And for global and mesoscale areas, yeah, so it's a good practice to use numerical weather prediction models as far as they provide the opportunity, yes, to have this external meteorological data like clouds, temperature, humidity, pressure, etc. So we just use the results, we extract the results from the meteorological data providers and use these results to produce the forecast of PV power plants output. For shorter perspectives, it's here. So we may use some like more advanced types of initial data, like satellite snapshots or even separate cameras, which give us the opportunity to analyze the state of the clouds. But for these time horizons, yes, so we may use machine learning methods, including artificial neural networks, ensemble decision trees, etc. So it's just the illustration of the existing approaches and technologies to be used for different tasks associated with photovoltaic energy forecasting. And it's very important to understand here that depending on the time perspective we want to take into account, we may implement different models and the input data may be different as well. So it depends to predict 1 minute ahead or 1 day ahead. So it's like a dramatic difference. And it also makes sense what kind of area are we considering? Is it a global area like a country, or is it just the energy production of the rooftop PV power plants of the household? So it makes sense, and please remember it. Well, this is some sort of the simplified flowchart, yes, of the PV forecasting system, which could be created within the framework of the summer school project case solution. Um, the very first phase, which is really important, and I always focus your attention on it, is the input data pre-processing subsystem. Well, this is just the enumeration of different initial data types which can be used within the framework of photovoltaic plants forecasting. But anyway, we have to keep in mind that we have to address this data processing carefully to select the most important features, to make some feature filtration, cleaning, elimination of outliers, etc. Typically, these processing actions are done within the framework of data processing subsystem. Well, this flowchart gives us the idea of how the PV forecasting system could be created. So it can be created separately by forecasting weather and solar irradiation, because actually solar irradiation is not provided in the predictions extracted from the outer weather data providers. So it means that on the first stage, yeah, so we may face the problem of predicting solar irradiation. And in the second stage, yes, after we have predicted solar irradiation, we may face the problem of predicting the solar power plant output. So we may divide these tasks into two. So it provides more flexible solution, because in case you have separate prediction of irradiation and solar power plant output, you may implement mm, some sort of flexible actions and, for example, take into account the service and repair actions of inverter groups, of PV panels groups, etc. But it can be done differently. So you may combine these two stages into one big stage and just try to find the relation of the input data and the photovoltaic power plant's output. So it means that you combine these tasks together and put them into the black box of machine learning algorithm. Um, well, you will not be able to make some flexible predictions when, for example, some sort of power equipment is out of service. But anyway, you will be able to find the relation of the input data set of the features yes, to the output variable, which corresponds to day-ahead power generation plan. Okay, so just one more time, yep, regarding the quality metrics of machine learning algorithms, so which could be implemented. So, and more maybe about the results that we want to get. At the left side, you see the formula for mean absolute percentage error, so which can also be used for PV forecasting quality assessment. But my suggestion for you would be to think about the appropriate quality metrics, appropriate error metrics, which could be used to assess the quality of the forecasting model. Because mean absolute percentage error will inevitably result in great errors in morning and evening hours, and it will degrade the overall quality of the model in general. So, for example, if you address mean squared error, yeah, so it's more, from my point of view at least, it's more adequate, yes, from the point of view of assessing the deviations of the forecasts from the ground truth provided in the initial data set. Before implementing machine learning model, I would like you to think about what kind of result you want to get as the output of machine learning system implementation. And the blue curve here stands for the ground truth. It's actually the measured value of PV power plant's output. The orange curve, maybe the orange chart diagram, stands for the 24 hours ahead forecast. The dark blue, yes, stands for 1 hour ahead forecast. So in our project case, we are not expected to produce 1 hour ahead forecast, but anyway, it is presented here for you just to feel the difference. Now I want to focus your attention on 24 hours ahead photovoltaic power plants generation forecast, and more likely to this very specific part of the curve under consideration. And well, it's very easy to see that during this part of the day, we have dramatic difference of the ground truth, yes, and the 24 hours ahead forecast. So what is the reason actually? The red curve presented here in this slide actually corresponds to the cloudiness, and cloudiness is the characteristics, yeah, so it's like clouds. It's provided in percents, and we collect this cloudiness data from external data source. So we just take this data from meteor provider. Um, Let's analyze the behavior of 24 hours ahead prediction model. So in these figures, yeah, you see that the model reacts adequately because the cloudiness grows. It means that the energy production from PV power plant drops down. So, and it's actually adequate. But from the point of view of comparing the forecast with the ground truth, we may see that for these starting hours here, the ground truth representing the PV power plant's output, so it increases, but we have the data that the cloudiness is growing as well. And well, actually, what does it mean? It means that we may have data from various data sources. The ground truth of PV power plant production is extracted from energy accounting systems installed at this very specific power plant. But the weather provider is an external company providing you the data set from outside. So it's just the model of the big territory with some resolution, yes, of this model. And we have this forecast for a big territory, but not for this very specific power plant. It makes difference, yes, between the different data sources. So they may vary, and sometimes they may not be combined together. So for this reason, please be attentive and put it to scrutiny when analyzing the correspondence of the model with the features. Yes, just analyze the behavior of the model and try to analyze the behavior of the output variable. Yes, which is the PV power plant energy production versus the behavior of the features that we have. And in terms of the features, for example, we have cloudiness. Try to compare and make the analysis. Is the data adequate? So, or something contradicts something. This slide illustrates the example of how it can look like as a result of developing PV plant forecasting system. And actually, this is a screenshot of the software package, and we were actually authoring the mathematical core of this prediction system. Well, actually, within the framework of the result, yes, that we have, this very specific sample day is characterized by sunny conditions. So the energy output during the day was about 86 yes, thousandths of kilowatt hours. So we've predicted about 80 thousandths of kilowatt hours too. The sunlight hours corresponded to the time range starting from 8 o'clock in the morning and 18 o'clock in the evening. Let's see how the model works for partly cloudy conditions. So as for me, it works quite great because practically we have correctly forecasted the total energy output during the day. But anyway, during some days we have some deviations, not so critical, but considerable. Now let's try to analyze how it works for cloudy conditions. So we are still fine with forecasting the total energy output during the day, but we have some greater distortions, yes, during the day of forecasted values and the ground truth that we observed during this very specific day. And attention, well, this actually was one of the misforecasted days with the application of this system. Well, actually, after that day, we were forced to make some updates to the mathematical core because analyzing the results, it's absolutely evident that we were lacking specific features. Because for this very specific day, well, actually, we had the same cloudiness conditions as for the previous days. But we did not introduce the weather events like rain, fog, the height of the clouds, etc. It all makes sense. And moreover, in our training set, we did not have the days corresponding to such weather conditions. As a result, so we mispredicted the energy output maybe 3 times greater. Yep. And well, moreover, yeah, so we misclassified the weather conditions and did not take into account specific features like rain and fog. So as a result, yes, of the analysis of the algorithm, and well, maybe it can be done in your case as well, I'm really encouraging you to try to make these forecasts for some sample days and visually analyze how the algorithm works. So it makes sense because as a result of machine learning algorithm training, you just get the mean accuracy. So it's just like average for all of the data set, but you have no idea on how it works for these very specific days. Sunny days, cloudy days, rainy days, snowy days, sandstorm, whatever. So please check these very specific sample days and look how it works. Well, now let's move on to lecture learning outcomes. Within the framework of today's lecture, we learned how machine learning can be used to solve multiple industry-oriented problems. So now you have the understanding and the vision what kind of problems can be solved with the help of machine learning. Please be attentive. Machine learning can be hacked intentionally or occasionally. For this reason, please be aware of hacking your own machine learning algorithms. For this reason, be careful with data, machine learning methods, etc. I would like to emphasize that you're expected to select proper regression model to deal with photovoltaic energy forecasting within the framework of your summer school project case. And the last but not the least point, that machine learning quality for photovoltaic energy forecasting is better to be visualized based on daily samples of PV production, not based on mean quality metrics of machine learning algorithms in general, but it's better when you show specific daily samples with standard weather conditions like sunny, cloudy, partly cloudy, rainy, etc. Well, thank you very much for your attention. Hope to see you next time. Bye bye, and good luck with the project case solution.